Okay, and it'll make a lot more sense after we watch another video too, because my 3D models are not always wonderful. Okay, so now if you have a lot of electrons and you can squish them around, left and right, and make them go in different locations of the molecule, then you can make it polarized. And essentially what happens with that is this Br2 molecule will end up going next to another Br2 molecule, and it'll get real fat on that side and kind of little on this side, because this guy went over here. Sorry, this looks weird now. Okay, this one forced the electrons, because there's just a bunch of negatives here, so they actually affected the right-hand side of the bromine, and they pushed the electrons this way. So now the left side of this is partially negative, the right side of this is partially positive, of that one. This one, left side of this is partially negative, right side of this is partially positive. So this is called a temporary dipole moment. It's temporary. It's not going to stay there for long. That's why these are somewhat weak in terms of all the IMFs in the world that we can deal with. So this electron they kind of sit over here for, I don't know, a couple nanoseconds, and they go back to their original position. Once they go back to their original position, everything is nonpolar again, hunky-dory, not attracted to one another whatsoever. So it's polarizable. We've made that polarized. We made it opposite charges. All right, so then we have another example. This is a really good example. You'll see this one, something like this probably on the AP exam. Contact between molecules. So I have drawn a couple different versions of pentane. So you don't have to know the names like neo and iso. Iso just means in the middle, like isosceles triangle. I can tell you that one. But the carbon chain is in straight chain here. It's got a straight with a branch here, and then it's got a T shape here. Okay. What's going to be able to get closest together to stack on top of each other? Which of those? So pretty much what you want to do is you want to have every molecule able to touch another molecule on the most surface area possible. It's hard to stack P's. What points are actually touching? That little bitty spot there and that little bitty spot there. Even if you stack them like this, there's a bunch of H's in the way, around here. You can't stack that very closely. This one, maybe you could stack it backwards. Okay, you got a little surface contact for this one right here. But this one's a straight line. Boom, 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 boom. You can stack straight lines much better than you can stack different shapes. Does that make sense? Okay, so it's like chemistry Tetris. So basically, if you can get a lot of stuff stacked on top of each other, you can force them to interact on more locations, and that's going to allow them to attract each other in more locations and make their attraction stronger. Those are just still lemon dispersion forces, but in more places. So increasing the points of contact is going to increase the force of this intermolecular force. And then I say helium because helium can interact with other heliums through that polarizability method. And then methane is a good example because itself is nonpolar, but it can do the whole stacking thing and start to attract to other methanes. But which of these, let's say methane or ethane, which of those is going to have a stronger London dispersion force? Take a guess. Methane or ethane? CH4 or C2H6? C2H6, what? Okay, so this is a carbon and this is a carbon chain. Okay, so this one can stack, yeah, well that one can stack too. There's more C's, there's more points of contact, I like that better. Also there's more electrons, so technically once they start stacking, they start polarizing each other. More electrons means you can have more strength of attraction. So not only do you need to know the order of strengths of these things, but you need to know how to explain them very well. We'll keep working on this. All right, DD. Dipole-dipole forces. These are only present in polar molecules. Only present in polar molecules. London dispersion forces can still exist in addition to the dipole-dipole, but what's the more significant of the two? Definitely the dipole-dipole, because both of them still exist in this molecule, because like I said, London's in everything. So if you increase the molar mass of something, generally that means that you're going to have stronger DD forces, or dipole-dipole forces. So dipole-dipole forces exist in things like this because I think we all can picture nitrogen trifluoride. I think we're good with like picturing the Lewis structures. What's the shape of this one? I'm gonna wait for one loud, proud answer. Trigonal pyramidal, right. It does look like a T, but T shape is not going to happen unless you have two lone pairs on the central atom. Okay, so that is definitely trigonal pyramidal. So what it ends up kind of shifting as is kind of like this. Big lone pair on top, right? Polar or non-polar molecule? Definitely polar. I don't care that it's got 3 different dipole moments pointing towards the fluorines. That's nothing compared to this big, huge dipole moment that's pointing upward, which is the lone pair. So the whole entire molecule actually has a dipole moment pointing upward. So there's a partial positive down here and partial negative up here. Okay, this polar dipole moment right here is going to then cause another nitrogen trifluoride to do the same thing above it, but its F's down here and this lone pair up there. So the negative region of this one is attracting to the positive region of the one on top. Sorry, this is negative and this is positive. So that's how this will interact. So a lot of times the heavier ones, they start to kind of clump together more, and those forces become more significant. All right, now the best, the strongest example of a dipole moment is a hydrogen bond. A hydrogen bond is just a really special dipole-dipole force. Cool? So it's just a really, really special dipole-dipole force that occurs in very special situations. So anything with hydrogen bonding has hydrogen bonding plus London dispersion. I used to say hydrogen bonding plus dipole-dipole plus London dispersion, but dipole-dipole and hydrogen bonding are essentially one and the same. It's just the hydrogen bonds are the strongest of all the dipole-dipoles. So it's only going to occur in the ones that the molecules, covalent molecules, that are polar. Still, they have to be polar, just like dipole-dipole was. Do I have that someplace? Still has to be with polar molecules. But those special bonds have to exist there. They have to be the Fon bonds. I don't know why I didn't put Fon here. Okay, H bonds are fun. F O N. Okay, they have to be H bonded with F, O, or N. That's it. No HCl. That's not going to be able to make a hydrogen bond force with another HCl. No HI. It's not going to be able to make a hydrogen bond force with another HI. But anything with these bonds will interact with other of its same identical molecule or other molecules that have these situations right here. They can interact with each other via hydrogen bonding, okay? So this is the strongest because of the Coulombic attraction that forms only due to the largest electronegativity difference. That's all it's due to. So actually, you guys have these papers in front of you. I think most of you guys do. I'll let these out from Honors Chem. Look at the difference between H and Cl on the electronegativity sheet in front of you. H, I think, is a 2.1. Cl is a 3.0. Difference? What's the difference? 0.9. That's polar covalent. Okay, that's pretty large dipole. Nothing crazy though. How about H and O? 2.1 and 3.5. Okay, that's a larger difference. This is what, 1.4? Okay, same thing for HF. HF would have 2.1 and 4.0. So this is 1.9. And HN, what's that difference? 0.9. Okay, so I guess the HN ones are actually weakest of all of them, but anything that has this biggest, this big electronegativity difference is going to have a large portion of the molecule that's negative and a large portion of the molecule that's positive. So ammonia, for example, it's got a large negative region here where the lone pair is, but also we've got these dipole moments that are pointing up to nitrogen. So not only is the negative making it partially negative, so are the dipole moments that are pointing upwards. So this is a big partial negative, and this is a big partial positive. Bigger differences make stronger attractions between this and the next one that does it. So I keep scrolling down here. The next one that does it will make the same situation. Partially negative, partially positive. So the bigger their differences internally will make a bigger difference in the force of attraction between these. So what's actually being attracted here? What's attracted to what? So the negative region of the nitrogen here, which is its lone pair, is attracted to, right, that hydrogen right there. That dash mark there is not a true bond. What is it? It's a hydrogen bond, which is an attraction. Not a true bond. Not like a covalent bond. It's a true bond. Cool? Right, so hydrogen bonds do not exist internally. Things exist between two molecules. Okay, so also increases with molar mass, just like it's just due to more electrons, and a lot of times it's the density of it, the electron density. All right, do I want to do, oh yeah, I'll do his video. Oh yeah, we'll do the video right now. All right, this is, if you want to take any notes on that paper I gave you, the two charts, I'm going to do the, let's do London first. I like the London one, so I want to do that one first. And the other one, we might do a second.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here.
Yeah.
Before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules and we move them apart a little bit, there are going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular between molecules. And they're going to be found in all atoms and molecules. So everything is attracted through London dispersion forces. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have two helium atoms, and so they're going to have two protons on the inside, two electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are two what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those two. It's fairly simple. It's going to hold them together. Now, it's just instantaneous. It's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area, so we're going to have greater forces.
I think it's easier to see it in that those space-filling models and the long chains, but that's essentially what you're seeing. This is long N-pentane straight chains, and that's the one that had a T shape.
So the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces.
What did he just say was higher? Boiling point. Why would boiling point be higher for something that had a higher force of attraction? I heard a lot of mumble jumbo. Make sense what you said. So the London dispersion forces are stronger. So why is the boiling point higher though? You have to overcome. I like the word overcome better than break. It sounds like you're breaking bonds, and that's really not true. So you overcome the London dispersion forces that are holding them together with more energy, higher boiling point. Okay, we're going to talk about that soon.
What else? The polarizability. And polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, and a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why, as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces.
So why is iodine solid then? Go for it, Allison.
It's got the stronger forces holding the
I2s together, right? So seriously, the strength of these things can get to be pretty large because it's making something go from more gaseous state to more solid states, pulling the atoms so close, or the molecules so close together.
As the atoms get bigger, they have more electrons. We're going to have more of this uneven electrons. And then finally, pi bonding. That's going to have orbitals that overlap. It forms something called a pi bond. If we increase the number of pi bonds inside those molecules, we're going to increase these London dispersion forces. So again, what are they? They're attractive in nature, found in...
It just goes back over the chart again. Okay, so let's talk about how these relate to physical properties. I'm going to do the dipole one at the end, okay? So this is what I was telling you. Those first ones are not true IMFs. You need to read about these a little bit more if you want to, but we just went over those first two dipole, hydrogen bonding, ion dipole, ion induced, dipole induced, and van der Waals, which is just temporary dipole, or London dispersion forces. Those I want you to read into some more. We're going to talk about more of them in our next unit, but you can pretty much tell what's happening. Ion dipole, an ion and something with a dipole. Give me an example of an interaction of something of an ion with something with a dipole. I got one right here. All right. Sodium ion and water. Chlorine ion and water. They have a really strong attraction. Another one, ion and induced dipole. Something is normally not going to be polar, but an ion comes in the room, and it's very negative or it's very positive. So it's going to either repel or attract whatever's on another molecule to force the electrons to go to the other side of the molecule or come towards it. So if I'm sodium and I walk into the room and I see a nonpolar guy right here, what's going to happen? All his electrons are going to be attracted to me. All right. So the ion-induced dipole, right? Dipole-induced dipole. Another dipole molecule, aka water, walks in the room. You got a molecule that's not polar. It's going to force some sort of movement of electrons. It itself has a dipole, and then van der Waals. So we're going to go into those in more detail later. All right. Let me go straight to. I'm not going to do the species right now. I'm taking longer than I wanted to. I'm going to go to solubility. Oops, I'm not sorry, solubility. Let's do boiling point. So draw these structures. Take a little chart, draw your structures. I basically want to make sure you can create a hierarchy of or a ranking system of the boiling points based on IMFs. So I think you can do ammonia at this point in your head. At least my goal is for you to. All right, is that molecule polar or non-polar? Polar. It's polar. There's a dipole moment, total molecular dipole moment pointing up because you got a lone pair up here, right? All right, so this is polar. What IMF is present then? Hydrogen bonding in this one because it's the most special type of dipole. If it's the special one, you got to say hydrogen bonding. How did you know hydrogen bonding, Daniel?
Because it's the HN bonds.
Right, it's the H to N bond, and so what's happening is ammonia is going to be attracted to another ammonia via hydrogen bonds. Okay, Water. Got that. Don't even have you can do that when you're asleep. Okay. Water, polar, non-polar. Polar. Now the polarity is a combination of two things. What two things have to be considered in your mind before you know something's polar? Say again?
The lone pairs.
Okay, so the lone pairs are technically repelling the other bonded pairs, so it's creating a geometry. So we have to consider the geometry, which is caused by the lone pairs doing their job, and if cancellation of dipole moments can occur. So if something has two dipole moments, they're pulling opposite directions, like carbon dioxide, it's going to be nonpolar overall because they're opposite in charge and or in direction and magnitude. Water's dipole moments, both of them point upwards. So that's like a total dipole that points upward, like that, like kind of through the molecule. So that's definitely polar because you had a whole partially negative here, partially positive here. Definitely polar. So I considered the geometry because it's bent, and there's no cancellation possible when something's bent. They're two different. They're kind of going in the same direction. So definitely polar. What is the IMF? Hydrogen bonding again. Okay. So notice we've got two hydrogen bonding ones. There's a difference though in the strengths of them. We'll get to that in a minute. All right. CF4. Shape. Tetrahedral. Polarity. Why is it nonpolar? Okay, the electrons are equally dispersed around the 3D sphere, and you know that because you know the dipole moments all point in opposite directions. Now, I know they're not exactly, anti-parallel to each other. Not exactly, because tetrahedral can't do that. But if they're pulling equally in all directions in the same dang bond, you better believe it's nonpolar. All right, so IMF. Oh, that scared me. Let's finish this real fast. IMF. London dispersion. Okay. This one. So it's ionic. So does it have a shape? No, it's got a lattice. That's it. Okay. This one is like magnesium, 2 electrons, plus chlorine with 1 electron, and I'm going to draw the other one up here. You can just put 2 if you want to. Okay, so the magnesium donates its electrons to the unfilled chlorines, so 1 to each one, and that's going to make magnesium 2+, and then chlorine is a full octet, but there's 2 of them. All right, so if you had to determine the strength of 2 ionic things, which we might have to, how would you compare 2 ionic strengths? Right, charge product. Charge product, which is the magnitude thing we'll do shortly. All right, phosphorus trichloride. Phosphorus 5 plus 21, 26 electrons. Phosphorus. So what shape is this one? Is that that's only 20, let's see, 8. Is that 26? Yeah. Okay. So trigonal, I'll write it here. Trigonal pyramidal, because that lone pair right there causes it to be definitely like a pyramid. So polar, non-polar. It's polar because it looks like a little tree, lone pair up top. It's got, if you got a lone pair, I almost guarantee you, almost, not all the time, it's gonna be polar. Polar, so dipole, or hydrogen bond. Right, because there's no H bonded to it, N, O, or F. All right, nitrogen. Polarity. Nonpolar, this thing, IMF. London dispersion. Sodium chloride. Huh? Okay, so it's got a lattice, and that lattice's charged product is going to be important for us. So anyway, the Lewis dot, those sodium plus chlorine with 7 electrons goes to Na plus, and then chlorine with 8 electrons, Na. All right, so of all the types of bonds, which is going to have the highest, have the hardest time being, melted or boiled or being pulled apart, period? Ionic. Okay, so ionics are definitely full charges, so they have full, attraction, so they're Coulombic attraction. Which of these is going to be stronger, magnesium chloride or sodium chloride? Because of the charged product, right? So we did a 2 charged product here and a 1 charged product here. So I'm going to put this as number 1 in terms of boiling point strength. This is number 2 in boiling point strength. What comes after ionic? Hydrogen bond, right. Now metallic could come if we just had some straight up metal. Metallic has a high boiling point as well. But we need to consider like things that are actually bonded together, not just a delocalized electron path. Yeah.
Is the charged product just the magnitude of 1, or is it both multiplied together?
It is the magnitude of the 2 charges that were used to make this. No, it's the charge of the 2 different ions. Yeah, not the summative charge. It's just the 2 at different ones. So this is a +1 and a -1. Okay. London. Oh no, I'm sorry. Hydrogen bond. So we have these 2. How do you know which one has a stronger hydrogen bond force? Okay, so difference in electronegativity and what else? Okay, I was going to go something simple. Grammage, 17 grams, 18 grams. Generally, increasing mass increases your electrons, which should increase your, even like polarizability almost. But I think that also the double lone pairs, and we just went over the examples of the electronegativity differences. So in every single case we talk about, water's winning, but I think the best rule is to go with mass. So this one's number 3 in boiling point. This one's number 4 in boiling point. So all of these are having, from the highest boiling point, the next highest, next highest, next highest. What's after this? Dipole, dipole. We don't have any other contenders. This is number 5, and we have 2 contenders. Okay, so who wins? Or how do you decide? What were all the things that affected?
More electrons are stronger.
More electrons, more contact, more polarizability. So let's compare the mass first, because that's what comes, you have more electrons with. So 19 times 4 is 76 plus 12, 88 grams per mole. And then nitrogen is 28 grams per mole. So obviously, no choice here. This is going to be more polarizable here. Even though this one's better stacking, this one's more polarizable, which is going to actually trump the stacking in this case because it has more electrons. Number 6, I think I'm at, and then number 7. Yeah? All right, so it's a process. When you are doing comparative physical properties, you have to consider their IMFs so much. Okay, so you got to draw the little structure, figure if it's polar, non-polar, and then go with from there, okay? And that's what you're doing in the lab. But I'm going to go ahead and tell you what's with their polar, non-polar. Okay, so I'm going to show you this. You guys have about 20 minutes that you guys can work on this. This is a pre-lab simulation. Simulation is actually not all that necessary. You can look here at the data for different compounds, look at their physical properties. And physical properties are things you don't need a chemical reaction to look at, right? So you got color, color, melting point, boiling point, conductive, non-conductive, pH kind of is a physical property. So stuff like that. So that one I think only has like 4 questions on it, but it's in your packet. Now I'll share it as online too. After that, I have 4 compounds that I have assigned to you and a partner, and you guys I'm going to tell you what the compounds are, but you're going to do some tests to verify its compound type. It's either going to be one of these 4: ionic, polar covalent, non-polar covalent, or metallic. So you need to be the master at testing the properties of these 4 types of molecules, or bond types. And because tomorrow you're going to be given unknowns, and you need to figure out which of the 4 bond types they are and their identity. There are ways to find the identity. Some of them are harder than others. Some of them have very distinguished features. Okay, so then I'm going to show you that today, but I want you guys to play and explore and try some things, look up stuff, Google, I don't care. Come up with some true tests that are going to help you identify the different compound types, and I'll help you with some of those today so you can do it by yourself tomorrow. Okay, you are partners. And oh, the reading's really good for the understanding, or it's like enduring understanding. So you should do that. But where did I put it? I put it on my website under homework for tonight, because after you decide on some tests, write those down, and that's your procedure for tomorrow. Like, test compound 1 by doing blah, blah, blah. If it comes out this way, hey, it's probably polar covalent or metallic, so forth, okay? So the explanation there is. Explanation to strengthen student understanding is really good to read this time. And then you do have to look up some MSDS sheets for the safety, but the groupings are here. Okay? I did 8 groups. You're working with a partner because this is very important for you to be able to do. So the more involved you are, the better you are. Okay, so you guys can look at this online too. But I put right here some extra help underneath that. So I got Chromebooks, I got our stuff. Let me show you what you are. Oh, I need this list. Where's this list at? There we go. I need this list. Come to the back. That was like, I was searching for somebody that could deal with me, man.
She was containing the Ebola there.
Let me show you the stuff in the back, and then I'll send you off to the corner. Right, group 1. Oh, everywhere. Now, yeah, I have them in order. I have them in order. So group 1 is Zoe. She's having Sarah. This is iodine. I'm not opening this unless it's that's why I called her. So I have two group. I've got these figures together and have them for the summation. Group 4, group 5, group 6, group 7, group 8. I have a couple people I want to meet that are correct.
Oh, I didn't see that.
If you want a Chromebook, I can get you another one. There's 8 groups. Somebody can have this station. I need to tell you what your compounds are. I need to tell you what your compounds are. And then those people who have less than 4, I promise I'll get you your stuff. So you do your pre-lab simulation first. Go to my website, do the pre-lab simulation or questions first. Website under tonight's homework, it's in your packet. Yes. There's a table, like 3 questions, I think.
Oh, there's 2 up top above it.
And then 2 below, or maybe it's 4 questions.